Cool. So we're starting 6.3. 6.3 is about ratios, and ratios have a lot of different parts. We started talking about ratios back in chapter 5 when we were playing with fractions. So along with ratios are going to come up percents and proportions are the biggest topics. And also scientific notation. So does anybody remember our definition of ratio back from the introduction to fractions? Remember that was one of our interpretations about what a fraction could mean? Can you think of any ratios that you might use in your existence outside of math class?
And like baking.
Baking, okay. Do you have an example? I was just thinking of baking myself.
Like if you're only making one batch versus 3,
Okay,
what
so
the
like,
recipe calls for.
so for example, like tripling a batch. Triple a batch. SP.
Or even just when it asks for like a third teaspoon or something.
Or just a fraction of a cup or a teaspoon, that's another good one, yep. Fraction of teaspoon, cup maybe. Okay. I was thinking, like for baking, I like to make pizza, and my pizza dough has one important ratio. It's a ratio of 1 to 3. And usually when we write ratios, we put like a colon in between. Sometimes we'll write it like 1 in the word 2, 3. Other times we'll write it as a fraction, 1/3. And that ratio right there is, for my pizza dough, water to flour. So it's a nice simple one with a 1 in it, because no matter how much water I put in, I need to put 3 times the volume of flour. Or I could look at it the other way. If I used 1 unit of flour, I do 1/3 that amount of water. So ratios can move in different directions. Anybody think of some other examples of ratios? Monica, do you like your drink today?
Mm-hmm.
It's good? They did it right? Okay, so that means they must have gotten some ratios right? Right, because if they mix that up, like if they put like twice as much of the syrup in there, would you like as much? No, right. So much of what we've worked with is, ratio pops up in there. Another example, I like the bicycle. Page. And I'm going to attempt to draw a bicycle here. Something like this. There's handlebars, and then there's a seat here, and there's pedals, and then there's this ring there, and then from the ring to the back, there's this chain, right? And then as I go pedal around that way, the bike shoots across that way. And so in my bicycle, there's some important gear ratios. So for example, in the front here, I have a big gear. And in the back here, I've got this little gear. And the big gear has 52 teeth on it. And the little gear has 13 teeth on it. And so there's a gear ratio related to that, so that every time I turn the pedals and those 52 teeth go around once, right, the little gear is going to be moved too, right? And that little gear is going to make the back tire move, and the back tire is going to make the whole bicycle move, right? So we have this chain of events that happens here. So can anyone guess, like if I wanted to look at revolutions of the big gear, to revolutions of the little gear, what that ratio might look like. So think about that for a second. Think about this picture. Think about me pedaling, the chain connecting these things, the big gear moving, making the little gear move. Write down what you think the ratio is going to be of revolutions of the big gear to revolutions of the little gear. There's several answers to this. A couple of them are right, but there's certainly some wrong answers that happen when people give this a quick glance. But think about it for a second. Write something down on paper. Like I've got two easy answers off the top of my head. One is 52 to 13, the other's 13 to 52. And then there's variations on those. And remember, they're directly connected by the chain. So every time there's a little movement of one tooth on the big gear, that's going to make one tooth on the little gear move. Because of the way the chain connects them. Because it's a direct connection. Anybody think they know a good answer here? Jamie, what do you think?
1 to 4?
You think 1 to 4, so revolutions of the big gear to revolutions of the little gear.
Yeah,
So we've got an answer of 1 to 4. Does anybody have a different answer? You all wrote something down, right? Nobody wants to say. Did everyone have 1 to 4? Did anyone not? Is it right? Now, the misleading thing on this is a lot of time people want to say, well, the big gear has 52 teeth, so 52 should come first, and the little gear is 13, right, because I referenced the big gear first. However, you got to think about the physical part of the situation here. For those 52 teeth to go around, every time one tooth moves in the front, one tooth moves in the back. So if the big gear makes if one tooth makes a complete revolution, there's a matching tooth in the little gear in back. How many times is it going to have to turn? You guys are so quiet. Come on, help me out here. How many times? 4 times. Yeah, so 15 over 13 52 over 13 is important. 52 over 13 is 4 to 1. And that just refers to how many times this needs to keep up. So the little gear is going to have to turn 4 times every time the big gear has to turn 1. So gear ratios are a little hard to think about. They're kind of reverse of what you first think because of the 1-to-1 ratio with the teeth, or 1-to-1 connection with the teeth. But yeah, in this case, revolutions of the big one to revolutions of the little one is going to be 1 to 4. That's the correct answer. So, anybody have any other examples of what a ratio might mean? Did anybody look back in the notes and remember what we said a ratio meant way back when we first looked at fractions? You don't have to look now, I just hoped you might already have looked. Okay. What we said a ratio was initially, when we first talked about fractions, was just a comparison of two quantities with division. I just realized I forgot to do a sound check. Hello, sound. Okay, good, we have sound. That's all it is, just a comparison of two quantities through division. Which is different than a regular fraction, because a regular fraction is a part of a whole. And the example I think I initially gave for this was, say, men to women. For students in this class, the ratio is 1 to 9. And this is not a part of a whole, right? It's a different way of comparing. Could a ratio be a part to a whole? The answer is yeah. I could do a different ratio. I could compare men to total students. In which case I would get a ratio of 1 to 10. Right? And they both tell slightly different stories, even though they're talking about the same people. So a ratio could be a part of a whole, but it doesn't have to be. It's kind of a slightly broader picture of using division, which fractions are one way of using division. And there's all kinds of things we can relate. Did anyone drive here today? Is anyone concerned about their speed? Sometimes I am. I tend to drive too fast sometimes. So a type of ratio is a rate. And a rate usually compares two different units. One of which is usually time. So types of rates that we work with are miles per hour, which is just a ratio of some number of miles to some number of hours. So we can use different words instead of to, sometimes the word per. Anyone remember what per usually means in math language? It just usually means divide. So in this case, per is literally miles divided by hours. I have a doctor friend, and he runs an office, and doctors in his office, they recommend they meet a certain amount of patients per day. And so that could be a rate. So a rate is just a kind of proportion. And maybe their ratio is 12 to 1. They're supposed to see 12 patients per day minimum. Other kinds of rates that we deal with, conversion factors, which we'll play a little bit with later. So conversion factors make rates when we say something like 12 inches is equal to 1 foot, would be one example. There's 2.54 centimeters in 1 inch. Is another example. And those are equations. To turn them into conversion factors, which are ratios or rates, we rewrite them as something like 12 inches divided by 1 foot. And so that's a rate of a different kind, not involving time, because for every 12 inches that's covered, we're also covering a foot. Okay, so the rate of change of inches per foot. Similarly, instead of that, we might want to write it as 1 foot over 12 inches as a ratio. And similar for the centimeters. It could be viewed as 2.54 centimeters per inch, or it could be 1 inch per 2.54 centimeters. And all of these different versions have their pros and cons. Depends what we're doing. So we're going to do a little estimation here. Anybody guess how tall I am? I'm not that tall, but good guess. Thank you, I appreciate that. I'm 5'8", okay? So what I want to do is I want to say, all right, let's take my 5'8" and convert it to centimeters. How many centimeters tall am I? Anybody want to take a wild guess how many centimeters tall I am? Come on, somebody take a wild guess. Help me out. Have fun.
154.
Excellent guess, 154 centimeters. So let's see if we're close. So I'm definitely about 5'8", pretty close. So we want to take 5 foot 8 inches, and we want to change that into some number of centimeters. So we're going to use those conversion factors to do that. Now, the first thing I need to do is decide, do I want to just work with feet or just work with inches? Because mixed numbers like this are kind of a problem in computation. So what do we want to do? Do we want to work with feet or inches?
Inches.
Inches? Okay. So then I would have to convert 5 feet to inches. Now, every once in a while, I forget, should I multiply or divide by the number I know? That's where these rates come in handy. So what I do is I treat that as 5/1, and then I multiply by a fraction, and I put feet in the opposite location. That means inches has to go in the top here. There's 12 inches in 1 foot. What this tells me is if I want feet to go away and I want the answer to be in inches, then I better multiply by 12. If the number ended up in the bottom, guess what I would do instead of multiply? Divide. Okay, you guys are so shy today. Come on, play along. So 5 times 12 gives me 60 inches. So now, plus 8, I have 68 inches. I want to convert that to some number of centimeters. And I can just use the conversion factor again, but this time I'm going to use a different factor. So 68 inches, put it over 1, multiply by a fraction with inches in the bottom, and the rate from the previous page was that for every inch, there's 2.54 centimeters. So centimeters goes in the top, and for every 1 inch, I have 2.54 centimeters. So this tells me that if I want inches to go away, and I want the measurement in centimeters, I should multiply. And so now it's calculator time. So Google, what is 68 times 2.54? Google says it is 172.72, and let's just go to the nearest whole centimeter and call it 173. So I'm going to say this is approximately wavy equals 173 centimeters. So a hint I could have given you when we were trying to guess at how many centimeters tall I am, in flat shoes, and these shoes are relatively flat, my belt is almost exactly 100 centimeters off the floor. And the floor to my belt is taller than my belt to the top of my head. So it turns out from the belt to my top of my head is about 73 centimeters. And we'll play more with the metric system next quarter. Did I tell you we get to play the metric Olympics next quarter? Are you guys excited? It's fun. All right. So another use of a conversion unit or a ratio is conversion units. Conversion units help us figure out whether to multiply or divide by information relating to types of measurements. All right, so with that in mind, I'm going to give you a more complicated one to try on your own. Anybody have a cell phone? Maybe? Yeah. Anybody ever look at the cell phone while you're in your car? Possibly while you're operating a motor vehicle. Okay, so that's a bad thing, and there's lots of reasons why it's bad. Did you know there's more accidents due to distracted drivers from cell phones than there are from drug and alcohol accidents these days? Okay. And a large number of the accidents that happen with motor vehicles aren't because of the motor vehicle necessarily, but because of a pedestrian on the phone. Anyway, let's suppose we're driving down the road, and we are going 30 miles per hour. So that's a rate. Now, miles per hour makes sense when I'm moving in my car. I have a feel for what that's like when I'm moving around in my car. However, if I'm driving through a residential neighborhood and someone's walking by, a more adequate measure for them is feet, the number of feet that go by. Like, for example, think about the width of your house. Would you measure that width of your house in miles? No, we measure it in feet, right? So one thing I wonder, if I look down at my phone while I'm driving through a residential neighborhood at 30 miles per hour, how many feet have gone by if I look down for 1 second or 2 seconds or 3 seconds? So that's what I want to know. So my question is, 30 miles per hour is how many feet per second? And so this is now a problem-solving exercise for you all. Now, we could just Google miles per hour, feet to second, but we're not going to do that. Okay, we're going to do it a slightly different way. I'm going to let you ask me for some conversion facts related to this, and then I'm going to give them to you. Like, what facts would be nice to know in order to make this conversion?
How many feet are in a mile?
Excellent, feet in a mile. So there are 5,280 feet in 1 mile. So we can turn that into a conversion factor. What other information would we like to know?
How many seconds are in an hour?
Excellent one, seconds in an hour. There are 3,600 seconds in 1 hour. Usually people ask me how many seconds are in a minute and how many minutes are in an hour, but Monica, thank you for going right to the point there. Good job. By the way, 60 seconds in a minute, 60 minutes in an hour, 60 times 60 is 3,600. Right. Those are the only two pieces of information you need to make this happen. So, write something down. My recommendation is you write it down the way I did. In this case, we would write 30 miles divided by 1 hour. And it turns out you can set up multiple fractions, one after the other, to make this happen. So you're going to write down 2 conversion fractions and see if you can come up with a feet per second on this. And then I'll write down my work and we'll compare. Feel free to ask a neighbor at any point. I guess I should come up with a number on the side here. And a calculator is definitely important. So there's different ways to do it. My first step would be to get rid of miles, since that's the first one I wrote down up there. Since miles started in the top, I put it in the bottom. That puts feet in the top of the other fraction. So now I know what to do to get rid of miles. To get rid of hours, it started in the bottom, so it has to go on the top, which means its partner on the other side of the equal has to go on the bottom. And so that tells me the 3,600 goes on the bottom. And the other important thing here is if there's a 1, multiplying or dividing by 1 is useless, so that's kind of pointless. So on my calculator, all I have to do is take 30, multiply by 5,280, and then divide by 3,600. And what do we get?
44.
44. And what does that 44 mean?
Feet per second.
Feet per second, yeah, because that's what I have not crossed out, feet per second. Yeah, 44 feet per second. So let's think about that for a second. Anybody get a text recently? Yes? Do you have your phone nearby, Olivia?
Yeah.
Can you turn it off for a second?
Like all the way off?
No, not all the way up, just turn the screen off.
Yeah.
Okay, so now what I want you to do is when I start counting, I want you to turn your phone on and check your text. Ready? Go. 1 and 2 and.
Okay.
Okay, You did it? Okay, so that was like 2.5, 3 seconds? Maybe 2 seconds if she was really fast. Did you actually read the text or just see that it was there?
Yeah, thank you.
Oh, that's a short one. I was just thinking, okay. So it's like 2 seconds. So 2 seconds is how long? How much distance would have gone by? 88 feet, right? Because that's in 1 second. So we just calculated 44 feet in 1 second. Okay, so I have multiple purposes to this. Don't drive distracted. Don't look at your text while driving. So if you're going 30 miles per hour, which some people do in residential neighborhoods, even though you're supposed to go probably 25 or less, if you look down for 2 seconds, you've gone 88 feet. If you look down for 3 seconds, what's that going to be? 132 feet. How wide is your average yard in a neighborhood? 50 to 100 feet wide. So you've just gone by a couple of houses. A lot can happen in that distance and time. So, something to think about. All right. Let's move on. Next. Similar figures. So similar figures in geometry are figures with the same shape. If figures have the same shape, then they have the same angles and the same order. If I think about like simple shapes, so I'm going to draw a rectangle, and I'm making my best rectangle here that I was attempting to draw about 3 inches that way and 6 inches that way. Here, I'm attempting to draw a rectangle that is 5 inches that way and 10 inches that way. I'm going to draw another one down here. That is my best 4. And then this way, I'm going to go 7. Are any of these shapes similar? Now, I'm trying to make rectangles. So that means I've got a bunch of right angles going on. So are any two rectangles the same shape? So would you say, and so for example, maybe I make one that's 1 by 10. Is that the same shape? So I would say yes and no. They are all rectangles, so they're the same shape in that regard, but they're not technically the same shape because I can't shrink one down or blow one up to make the other without distorting it. Okay. So one way to think about similar figures is not only do they have the same angles, but sides have similar ratios. Sides have spelling ratios. So an example here, these rectangles all have a base and a height. So if I wanted to look at the ratio of base to height, rectangles are said to be similar if they have the same ratio. So my first ratio was 3 to 6, base to height would be 6 to 3. 6 to 3 can be reduced down to 2 to 1 or just 2. Do any other rectangles here have a base to height ratio of 2? Which one? Yeah, the 10 to 5 one. So these two, let's highlight them, would be classified as similar because they have the same ratio of base to height. So here, if I take the base, divide by the height, 10 over 5, gives me the same result too. But the other two are different. Now, what I was thinking when I was made the 4 to 7 one is I just added 1 to the 3 to get 4, and I added 1 to the 6 to get 7. So my ratio there of base to height was 7 to 4, which does not equal 2. So that's not similar. And so the way to think, another way to think about similar is if you shrink something or you blow it up, and you can make the same figure without distorting it. Right? Shrink or blow up or magnify without distortion. Anybody ever do any graphic or web design in here in prior classes? Anybody ever hear of the term called aspect ratio? Talk about that next. So aspect ratio is a term from graphic design. Graphic design is part of web page design these days because there's a lot goes into making a website attractive. And the aspect ratio of a figure in graphic design is the ratio of the width to the height. So width to height. Common aspect ratio for photos is 6 to 4. And that one always caught me by surprise, because if you think about that as a fraction, as a math teacher, I would rather write that as what? 3 to 2. Yeah. But for some reason in the graphic design industry, they decided they wanted to call it 6 to 4 instead of 3 to 2. Like, has anyone had photos professionally printed recently? 6x4 is a popular type for getting framed images. Can anybody think of some other ones that are popular? 8x10 is another popular one. So for photos, there's many aspect ratios. So 8 to 10. Let's see, I should go the other way. Eraser. 10 to 8 would be the way we write it, because we usually do width then height. But it could go the other way, because there's landscape versus portrait. 8 to 5 would be another one that's kind of common. So although 6 to 4 is popular, there are other ones. Is a 8 to 5 or a 10 to 8, are they similar to a 6 to 4? So when we talk about ratios, similar basically means equal. Is 6 to 4 the same as 8 to 5? No. And we could double check that. So to double check if ratios are equivalent, what we do is set them equal and cross multiply. 6 times 2 is 12, 4 times 3 is 12, so a 6 to 4 and a 3 to 2 are the same ratio. But if we tried the same thing with something like an 8 to 5 versus a 6 to 4, when you cross multiply, 4 times 8 is 24, no, what is it, 32? And 5 by 6 is 30. So we have 30 versus 32. They're not the same. They're not too far off. It might be hard to look at them both at a distance and decide if they're similar or not. But they're not similar since cross-multiplying leads to different results. So if you ever want to get a poster made or a postcard made or a business card made, the aspect ratio matters because postcards are a certain size. Business cards tend to be a certain size. Posters tend to be a certain size. And if you have the wrong aspect ratio, then things can go wrong. Either they have to crop the sides or the top, or they have to add space to the sides and the top. So it is a big deal when you're designing graphics. All right, so let's see, what time is it? 43. All right, let's do, actually I want to go over one more thing and then we'll do an activity. So we'll come back and play with some more ratios. We're going to move away from ratios for a second to percents. And if you could do me a favor, just write down what you think percent means. And give an example of it. Seriously. Fix the printer and it broke again. All right, so anybody want to tell me what percent means? Okay, Monica.
Yeah, I think percent means an amount of something. So
What's
like,
that?
An amount of something, so like 30% off of the $10 purchase.
Amounts. Off. Oops. $10. All right, anybody else?
Put a percent as a part of a whole, and then in parentheses I put 100.
Whole 100.
And then I drew a picture of five longs, and then I colored, I shaded in 2 of them, and then I put 2 over 5 equals 40%.
5 2 of them. So 2 out of 5 is 40%. Okay, cool. So with those two ideas in mind, what does per mean when we were talking before?
Divide.
Yeah, per literally means divide. Or divide by. What does cent mean?
10.
Not 10, you're close though.
1.
What is it?
1.
Almost. So other way, 100. Yeah, think about a cent. As far as money goes, is 1 out of 100 in a dollar. And so cent really means 100. So the word percent literally means divide by 100. So when we write 40%, now look at the symbol percent. What do you see right here? That red mark.
And divide.
That's a division. And what do you think these two things are right there?
Your 2 zeros.
They're the 2 zeros from a 100, yeah. So historically, you know, a computer was originally a person that did calculations for you. So you'd go to this business office, like an accountant's office, and you say, I need a computer, and this guy would say, what can I do for you? And he would make calculations for you. And they used to do a lot of calculations that divided by 100. They were just sick of writing divide by 100, and so some people got lazy and started writing it that way. And it caught on. And it's literally that simple. This is an abbreviated divide by 100. They just took the 1 out and put the zeros around the bar. So anytime you see the percent symbol, like 40%, you can literally just replace that symbol with divide by 100. And then you have two choices. You can do division, or you can simplify a fraction. So let's try both ways. So new page, 40% equals 40 out of 100. I'll write it as a fraction first. Can we reduce that? If so, how?
Divide by 40.
Not 40, that's too big. We could divide by 10. Yeah. So I could divide top and bottom by 10. And remember back on one of our previous tests, I recommended when you're reducing fractions, write down what you're doing. Don't just think it. 40 divided by 10 is what? 4. 100 divided by 10 is 10. Oh, my goodness. I must have hit a button. What did I do? Look at my page. Hang on, technical difficulties. Undo maybe? Oh, there is no undo. Weird, what just happened? Thank you, Josie. Oh, I don't know what happened. Okay, let's go again. Let's see. We have 40%, which is 40 over 100. We divided 10. And that gives us 4/10. And then what are we going to do?
Divide again by 2.
Divide by 2. And again, when it matters, when you're taking some kind of assessment, write all this down. 4 divided by 2 is 2. 10 divided by 2 is 5. So we get 2/5, which is what Jamie started with, right? The other way we can think about it is actual doing division, in which case we want to take 100 into 40. So does 100 go into 40? And so our trick there is to put a decimal where it exists, write that decimal above, and then add a 0. So I'm going to make a note, the decimal point there. 100 goes into 40 0 times. I like putting the 0 in front. Does 100 go into 400? How many times? 4. 4 times 100 is 400. Subtract and get a 0, so I'm done. This must be 4/10.
Are we kind of going to get complicated, like when you have 40% off of like an item that's like 26 something? Or...
Yeah, we're going to get to that. Yeah, so we're going to do more complicated percent increase, percent decrease. Yeah, and I'm going to show you ways to draw pictures of those that helps make them more clear.
Okay.
Yeah, excellent question. All right, so long division isn't everybody's friend, so we've observed some patterns. Like when we divide by 10, what happens to the decimal? We talked about this a couple weeks ago. If you divide something by 10, for example, 4 divided by 10 is equal to what?
0.4.
0.4. So there was a hidden decimal, we'll call it right here, and that decimal moved once. I had 40 over 100. There was a hidden decimal right here at the end of 40. Where did that decimal end up? 2 places over. So every power of 10 we divide by shifts the decimal once. So here's 1 power of 10, 2 powers of 10. This decimal got shifted twice. This one got shifted once. So a shortcut to dividing by 100 is shift the decimal twice. Let's make a note of that. dividing by 100 should make it smaller, so we move the decimal twice to the left. And that came up when we were looking at powers of 10. Does anybody remember which power of 10 we get when we have 100 in the denominator? The negative 2 power. Yeah, negative 2 power. So this is super important. This is like the highlight of the percent section. Percent just means divide by 100. So if I have a percent and I don't want it to be a percent anymore, I just divide by 100. And we have two options for doing that. We either use division, which takes us to a decimal, or we just reduce a fraction and we leave it as a fraction. Sometimes we want fractions. 2/5 is an okay number. 4/10 is another okay number. There's two different ways of dealing with it. So there's going to be a couple homework problems where given a percent, we're going to convert to a reduced fraction, but sometimes we'll convert to a decimal. Now we also want to go the other way. If changing page, so just a note, when we change from a percent to a regular number, and I'm calling it a regular number because the percent symbol goes away. If the percent symbol's there, it's not a regular number, it's a percent. If the percent symbol's gone, it's a regular number. So to convert from a percent to a regular number, we divide by 100. So that's a rule, that's an algorithm. Why do we do that? And the answer is super simple. It's on the first page here. Why do we do that? Because what does percent mean? It just means divide by 100. That's it. It's like, why do multiplication problems come out the way we do? Because multiplication means area. So why percent literally means divide by 100. They are synonymous. So suppose I want to change a regular number to a percent, which we often need to do. Anybody want to take a guess as to what we do? We don't divide by 100. Multiply by 100. Yeah, that's that simple. So change a regular number to percent, multiply by 100. And a slight twist to that, we're actually multiplying by 100%. What is 100% as a regular number?
Whatever the whole number is.
Nope. Sort of. Sorry. Okay, what does percent mean?
Divided by 100.
Divide by 100. What happens if you take 100 and divide by 100? What do you get?
1.
Yeah, 100% is just 1. So it is a whole number. It's the whole number. It's 1. And so when we're changing a regular number to a percent, we're really not changing the number because we're multiplying by 100%, which is really 1. What happens when you multiply by 1? It's the same number. Yeah. So let's go back to Jamie's example of 2/5. So 2/5 is a regular number. It's just some fraction. If I want to change that to a percentage, I'm actually making a number that's equal. And I make that number by just multiplying by 100%. These two are equal because 100% is 1. I'm just multiplying by 1. I'm just doing it in a clever way. Now all I need to do is clean up that part. Okay, so let's see. Cleaning up that part right there, I could look at that as 100 over 1 as a fraction. And then 5 goes into 100. So I could say this is 2 times 100 over 5. The percent symbol's still chilling out there. But 5 goes into 100 how many times?
20.
20. 20 times 2 is
40.
40. So this must be 40%. So what we do is we multiply by 100%. We hold the percent symbol and we clean up that arithmetic. Whether we do that by hand or calculator, it doesn't matter. We just some way we do it. Anybody have a savings account?
No, I had to get rid of mine.
I have a savings account, and I don't know if you guys know this, but like 10 years ago, the housing market crashed. And after the housing market crashed, the Federal Reserve, which is like the Bank of the United States, dropped interest rates so much that interest went way down for things like buying a house. So it used to be like, to buy a house, you had to pay like 10 or 12% interest. Then for a while, it was like 3, 4, 5%. Downside is savings account rates went down too. So 15 years ago, you might have been able to get a savings account that paid 2 or 3%. Today, you're probably going to get 0.5%. Okay? So I put $1,000 in there, I get 0.5% of $1,000. What is 0.5%?
Almost 100.
Well, what does percent mean?
Divide by 100.
So I have to take 1/2 and I have to divide it by 100. Okay, well, I could look at 1/2 as a decimal. What's the decimal version of 1/2?
Sorry. It's
0.5, or, not slang, would be
5/10.
5/10. So this is the same thing as 5/10 divided by 100. And we just learned the trick that divide by 100 shifts the decimal 2 places to the left. So I need to throw 2 more zeros in between the 5 and the decimal. So it would be 005. How do I properly read that number?
5,000.
This is really 5 thousandths. So for every $1,000 that I have, I get $5.
That's sad.
What if I only had $100? How much would I get?
5 cents. No, 50
Almost.
cents.
I would get 50 cents. Yeah, for every 50 cents for every $100. Each year. So I give the bank $1,000. At the end of the year, they say, "Thank you for that $1,000. Here's $5." Okay, it's not Wall Street, unfortunately. So we do deal with fractions of percents. They come up in a lot of different places. They come up with raises. They come up with interest in loans. Often if you buy a house, your interest rate's not going to be some nice number like 4 or 5. Like my last loan was 4.9% when I got a mortgage on my house. It's less than 5. All right, I guess that's good. Okay. All right, let's take a break. We've been going at this for a while. I'm going to pause the recording here. You need to stand up and stretch or get a drink. We're going to do a little activity, part of one from the book. Where's my recording software? Hello, recording software. It's missing. So we're going to come back, those of you looking at this online, and do activity 6.3, at least parts of it.